Let's move right now into our interview with Peter Liu. Welcome on, Peter.
Hi, good morning. Thanks for giving us the opportunity to talk about the wonderful things that are going on with our experiment on the space station.
Well, we're really happy to have you here, and we know that things are going on this week on board the International Space Station. Could you start off and tell us a little bit about the experiment that you're working on?
Sure, I'd be happy to. So we're looking at how liquids and gases interchange into each other in zero gravity, or in microgravity. And so what we've done is launched a series of different samples that have sort of the analog of liquids and gases all mixed up. Kind of like you have like a soda, right? And you, or pop, I guess, this is for you guys in the Midwest. But when you unscrew the cap, the gas leaks out. And in general, when you have mixes of liquids and gases, particularly of the same substance, the liquid is always heavier, so it falls to the bottom of the container. You don't have, for instance, the gas out of a decompressing soda sinking to the bottom and the liquid coming out of the top. So the nice thing about going to microgravity is that those density differences don't matter. And so now you have the liquids and the gases separating from each other, but one doesn't always float to the top over the other, and we can actually look at the structure of that process.
Well, that's very interesting. Can you tell us a little bit about what specific activities are going on this week with the experiment?
Yeah, so we have these mixtures of, consider it sort of like a liquid and a gas mixed together, and the astronauts mix them up, and then they want to separate. So what we've had them do is take photographs of this sample as it's separating over time. And we can then download the images from space and take a look at the structures that are forming and then understand a bit more about the fundamental physics that's driving this process.
And really, what in simple terms are you trying to learn?
Well, we want to understand a more fundamental question of what happens when liquids and gases try to separate from each other. So there's different kinds of patterns that form. They form structures that grow, and we want to measure how quickly those structures grow, in particular with this experiment.
Okay. I know you don't have any full results on this yet, but have you seen anything interesting?
Yeah, we've seen a lot of interesting things. This is BCAT-6, but this is the fourth in a series of experiments going back to BCAT-3, and with each iteration we've learned more and more. And I think maybe the biggest message is that a lot of the predictions of these systems that were made by theoretical physicists and chemists over the last 10 or 15 years based on samples that undergo this process on Earth, well, when we go to space and we take gravity away, we get some different results than we expected, and that's a much more fundamental measurement, if you will, of the behavior of the system.
And does the space station environment give you a good microgravity level in which to do your experiment?
Yeah, the space station, I think, gives us much more than just a good microgravity environment, but a fundamentally new type of environment that allows us to do an experiment that there would be otherwise no way to do. And it's not just the microgravity, but there's two things I think that the space station gives us on top of that are important and unique. The first is that it's a stable platform. You know, our phase separation experiments, we can take photography for months, and there's no real way to do that in any other environment. So the space shuttle, for instance, it was a great platform, but it was only ever up in orbit for a couple of weeks. So if we're watching this liquid and gas separate from each other over the course of, say, months, there wouldn't be any way to do that physically without the space station. And the second major aspect of why the ISS is so important for what we do is the fact that there's such talented and hardworking crew on board. And so when we launched the first iteration of this experiment in 2004, we weren't really sure what we were going to find. So we took some pictures, but through half a dozen or a dozen different astronauts improving it, we're now able to measure things. The photography is so much more precise, and therefore we can do much more careful analysis on the data that otherwise wouldn't have been possible. And this is, I think, speaking to the strength of doing experimental science with crew members, a lot of whom have PhDs in science and engineering, and they're the ones that are actually innovating the experiment, making it better, allowing us to see things that otherwise we wouldn't be able to see. So I think both the long-term stability and the presence of very smart, very talented, very hardworking crew gives us the ability to do science on ISS that otherwise just wouldn't be possible.
And you mentioned that there have been multiple different versions of this experiment. I guess being able to tweak your experiment may be helpful as well.
It's much more than helpful. It's absolutely critical. And in fact, we've gotten, I don't know, 100 times as much more data and at a much higher resolution just by improving the photography, or I should say the crew members improving the photography based on relative to what we originally thought we could see. So it's much more than just a minor detail. They're the ones that have actually innovated the experiment. And I think it's kind of easy to see why, because we can't do these experiments on the ground. The liquids always sink below the gases, and you don't see any interesting structures. You have to go to orbit in order to see these things. And there's no way that I on the ground can predict what it's going to look like, which is why we flew it on the space station.
Well, what's your background? Where are you from? Where did you go to school? And where are you working right now?
Okay, so I'm a postdoctoral research fellow at Harvard. I did my PhD actually partially on this experiment because it's been a while, also here at Harvard. I did my undergraduate degree at Princeton, and all of my degrees have been in physics.
Peter, I want to thank you very much for being with us today. In the meantime, good luck with your research on the colloid research and your time in Harvard. I hope you don't get snowed on too much today.
All right. Well, thank you very much. Thank you very much for this opportunity. And we really have to thank the crew, Dan and Don. This increment have done just a wonderful job in getting us fantastic data. And we want to thank them and look forward to our last sample running next week.